Okay. Can you hear me now? Okay, thank you. So so we say that a rational number is dyadic if it is of the form p over 2 to the k, where p is an integer and k is a non-negative integer. So those are interesting numbers because in numerical computations on a computer, you often represent numbers in let's say floating point arithmetic, and so we are really interested in finite binary representations. And so the question is, okay, if we want to solve linear programs exactly, we might want to require that the numbers are dyadic numbers. So we're going to look at dyadic linear programming, so standard LP, where in addition, we would like our solution vector to be dyadic. And that means every component of the vector, solution vector, is a dyadic rational. Now, if we were going to require finite precision, if all the numbers are of the form p over 2 to the k, where k is bounded, then we're back to classical integer programming. But here, the twist is we are not restricting the number of digits. We're just asking that the representation be finite. We just want a finite representation in binary. Now, our motivation came from a conjecture of Seymour. So here's the here's the conjecture. So we look at set covering again. So A is going to be a 0-1 matrix, and now we're looking at solutions to AX greater or equal to 1, the vector of all ones, X non-negative. I'm going to look at, let's say, a minimization problem where my objective function is some integral vectors W. And so if you look at the LP and its dual, you of course have this equality. And so we might be interested in trying to understand the dual solutions, which is kind of a packing of the rows of this matrix A. We're going to say that this matrix A here is ideal if the polyhedron here only has integral vertices, or said differently, for every objective function W, we can make it integral. For every integral objective function W, there is an integral primal optimal. And Seymour made a very intriguing conjecture in the 70s, saying that if this matrix A is ideal, then the dual always has an optimal dyadic solution. So for every integral W here, this fractional packing problem. So the primal is integral. And W is integral. So the objective value here is an integer. But of course, in general, the dual will have a fractional optimum solution. And so Seymour was interested in understanding the fractionality in this dual. And so his conjecture is that, in fact, the dual always has an optimum solution that's dyadic when W is an integral vector. so that was actually what motivated us to look at this kind of dyadic question. And we've kind of been thinking about this conjecture of Seymour. We were able to prove it in a couple of cases. We were able to prove it when the LP solution is 2. If the objective value is 2 here, we can show that actually the dual always has an optimal dyadic solution. We also proved it when the rows of A are this combinatorial problem. They are the T-join of a so-called graft. Okay, I'm not going to get into that, but yeah, go ahead. Yeah.
I mean, like this, like having optimal value 2 is not really preserved under scaling the value. So what do you mean? It's unweighted or?
Yeah, non-negative weight. Oh, okay. Yeah, I should have said non-negative weights. Yeah, sorry about that. Yeah, yeah. So yeah. So I mean, yeah. So it's really it's really when W is kind of a 0, 1 vector, really. Yeah, or all one vector. Okay, so yeah, and Seymour, of course, made other kind of famous conjectures about this. I mean, there is this sort of quarter integral conjecture that he has, which is of course a stronger statement of this conjecture when the matrix A is the T joints of the graph. Yeah.
So coming back to what's that sense, so this means that the objective, the optimum value is 1, and the conjecture is also true.
Gerard, can you please repeat the question?
So when the objective, when the objective vector is W of all ones, right?
No, I mean, if the optimum value is exactly 1.
Oh, okay. Yeah, it's true as well. Yeah. Yeah, it's true as well. Yeah. Yeah. When the objective value is 1, it's also true. Okay. So so here are some questions that one might ask about dyadic linear programming. When is the problem feasible? And if it is feasible, when does it have an optimum solution? Can feasibility be checked in polynomial time? Can dyadic linear programs be solved in polynomial time? Okay, can we also guarantee that the dual, or under which conditions can we guarantee that the dual also has a dyadic optimum solution? So these are some of the questions that we address in our paper. So let's start with feasibility. So notice that a dyadic linear program may have no optimum solution. For example, if I'm saying, this is just a one variable problem, I'm saying 3x less than or equal to 1, x dyadic. Well, I don't have an optimum solution in this case. In fact, I might not even have a feasible solution at all. If I'm saying 3x equals 1, x dyadic, I don't have a feasible solution. Okay, so those, so going back to our question about feasibility, if a dyadic linear program is infeasible, can one provide a certificate of infeasibility? You know, that would be kind of the first question that we might want to consider. Like, you know, that's one of the nice things about linear programming is, you know, you have this certificate. Okay, we're going to actually answer this question in the affirmative. And in fact, we then, you know, as a result, show that dyadic linear programming is in fact in NP intersection co-NP through this certificates. But in fact, we're going to show that in fact it's in P. It's polynomial, solvable. Okay, so let's look at feasibility. So here is the lemma. We're going to start with linear equations. We are looking first at a system AX equals B, where let's say A and B have integral entries, or more generally it could be rational, but let's make this integral. And then the lemma says exactly one of the following statements hold. Either AX equals B has a dyadic solution, or there exists a vector Y such that, you know, you can do combinations of the rows so that you get an integral vector. But if you do the same linear combination on the right-hand side, you get a non-dyadic value. Okay, and that's very similar to some of these certificates that Farkash lemma and for example, this so-called integer Farkash lemma is the following statement. It's the same hypothesis, and it says exactly one of the following statements hold. Either AX equals B has an integral solution. Here we ask dyadic. Or, you know, there exists a vector Y such that, again, if you make linear combinations of the rows with this vector Y, you get an integral vector, but the same combination on the right-hand side gives you something that's not integer. So it's very, very reminiscent of the integer Farkash lemma. Yeah, there's a question.
Yeah, just to check, you don't necessarily need A and B to have integer entries for this to be true. Or?
Yeah, that's true. Yeah,
Okay.
we could say rational. Yeah, but it cannot be just general reals. I mean, you have to have some kind of you have to have some kind of assumption on the coefficients. Okay, so yeah, let me give you a quick idea of how this would be proved. So I restated the lemma here. And first, let's observe that both 1 and 2 cannot hold simultaneously because if the first holds, AX equals B has a dyadic solution X, and you also have a vector Y such that, this is integral, then, let's just look at Y transpose B. So we said B is AX. So you replace, and and then you can look at it as Y transposed A times X. Well, Y transposed A by hypothesis is integral, and X is dyadic. So you do the multiplication. The sum of dyadic numbers is dyadic, and so forth. So this is a dyadic number. So 1 and 2 cannot both hold at the same time, clearly. And now let's suppose that 1 does not hold. That is, AX equals B does not have a dyadic solution. Then, okay, if AX equals B has no solution at all, then that's the standard Fredholm lemma or Gaussian elimination, whatever. And so we So in that case, there would exist a vector y such that you can get 0 on the left-hand side and something not 0 on the right-hand side. And by scaling, you can ensure that, in fact, the right-hand side is non-dyadic. So that settles this case. So now let's look at the other case where AX equals B has a solution. Okay, so, but I'm assuming that I'm assuming that one does not hold. So AX equals B has a solution, but it doesn't have a dyadic solution. So how do we proceed in that case? Well, if you know the proof of the integer Farkas lemma, we proceed in the same way. And that is, first thing we do is we transform our equations into Hermite normal form. So, so we can assume that A has full row rank, and then we can bring A into Hermite normal form by doing elementary unimodular column operations. And so you can think of your so A can be written as kind of H times some unimodular matrix U, and then you look at the solutions of X and the solutions of this H times Z equals B, and and there is a one-to-one correspondence between you can go back and forth between X and Z through this unimodular matrix, because the inverse of a unimodular matrix is also unimodular, and so so that's basically how you do the proof. But what is interesting is you see how this kind of Hermite normal form plays an interesting role in this theory, which may not be obvious when you start thinking about it. Okay, so I'm not going to say more about this. And maybe the key lemma here is that a non-empty rational polyhedron contains a dyadic point if and only if its affine Hall contains a dyadic point. So, I started looking at some linear equations, and that's the main reason why, because this lemma tells us that actually I can just look at the affine Hall AX equals B, that contains that polyhedron, and the lemma says that the polyhedron contains a dyadic point if and only if the affine Hall contains a dyadic point. And the proof is not that complicated. I mean, okay, so the affine Hall contains a dyadic point, and now you look at a point in the interior, in the relative interior of the polytope. Take a rational point in there, and now let's look at the line segment between these 2 points. And there's going to be some rational vector, which can scale up to some integral vector. And now I can go along this line from my dyadic point to as close as I want to my rational number using, the point is that dyadic points are dense. So, I can go along these lines. I have 2 dyadic points. I have this original one, and then I have this one plus the integral vector. And in between, I have, it's dense. So, so that's basically why I can find a dyadic point within the polyhedron. Okay, but there's just kind of a quick thing. So, but essentially, what this gives us then is let P be a non-empty rational polyhedron whose affine Hall is AX equals B, then exactly one of the following statement holds. either P contains a dyadic point, or there exists a Y, like we had before, such that as you do this combination of the rows of A, you get an integral vector, and the same combination on the right-hand side gives you a non-dyadic vector. So, so that's for the feasibility part. And then we can just talk about optimization. And essentially, the theorem is that dyadic linear programming can be classified as either it's infeasible, or it's unbounded, or it has an optimum solution that all looks like very much like standard LP. But there's also a fourth situation, and that is that the dyadic LP is not unbounded. It has feasible solutions. It has a finite optimum value. You know, this is a supremum, but no optimal solution. And so yeah. So in cases 3 and 4, the value of the dyadic LP is just the maximum objective value in the underlying LP. So then you get this kind of complexity results. The feasibility problem for dyadic linear programming can be solved in polynomial time. And that's essentially, you know, this kind of Hermit normal form type of argument that that we made. You know, so this is polynomial that leads to a polynomial algorithm, and then we also get that dyadic linear programs can be solved in polynomial time, and that's kind of a combination of standard LP. Polynomial algorithms, and you know, this other aspect that we need to check feasibility, but we know how to do that in polynomial time. So so yeah, so that's very nice. Everything is polynomial. So now. You know, one question that is kind of very interesting to us is, okay, so what about the dual? You know, can we impose dyadicness in the dual solutions? So we're going to say that a linear system is totally dual dyadic. You know, very similar to totally dual integral, but now we're just there's a small twist here. So we're saying for every integral objective function W that we might want to put in the primal, the dual problem here has, if it has a solution, it has a dyadic optimal solution. Yeah.
Question. So, I mean, would it, if you have such a totally dual dyadic system, I mean, would you expect that like the dyadic denominator has a universal bound?
So yeah, so those are good questions. Well, okay, so and that actually ties into even the kind of the previous question. Yeah, we to prove polynomial algorithm here, we need to show that the denominator, you know, the 1/2 to the k is
sorry, I meant not dependent on W.
Yeah, right.
So like, is there, you know, for any W, is there sort of like yeah, over all W is the worst case dyadic denominator that you can get, like bounded? I mean, I would expect
yeah.
Yes,
So yeah,
like,
so we do have some. Let's see, we do have some bounds that that only depends on the size of the coefficients in the matrix. Yeah. Yeah, we do. Yeah, so we are able to show that the following are equivalent. A linear system is totally dual dyadic, and for every non-empty face, the tight rows of A at that face form what we call a dyadic generating set for the span. And of course, we could also talk about dyadic generating set for the cone, that because we're talking about inequalities here. But because we were able to go from polyhedra to the fine Hall, we can also get this result. Okay, so again, let's try to parse this. For every non-empty face of this polyhedron, the tight rows form a dyadic generating set for the span. What is that? We say that a set of vectors is a dyadic generating set for the span if every integral vector in the span of these vectors, every integral vector in there, can be expressed as a dyadic linear combination of the vectors. Okay. And what is nice about this property is that we can actually check it in polynomial time. So, so we have a certificate. We can check, that a system is totally dyadic, and we have a certificate. So it's in CoNP. Okay, and I'll just finish with two open problems, and there are many more, but an interesting direction might be, okay, what about more generally dyadic convex programming? Because one of the nice things is that our fine Hall lemma saying that, if a polyhedron contains a dyadic point, polyhedron contains a dyadic point if and only if it's a fine Hall contains a dyadic point. That's actually more general. And in fact, a non-empty convex set with a fine Hall is a rational space, a fine space. So a non-empty convex set contains a dyadic point if and only if it's a fine Hall contains a dyadic point. So, so the same nice relationship holds. And so, so that begs the question, okay, what about more generally dyadic convex programming? And then, of course, Seymour's conjecture is something that we'd like to understand better. That's it. Thank you very much.